So in the last lecture, we saw some basic properties of the elementary measure, and these are very nice properties, and they follow our geometric intuitions very nicely. For example, translation invariance, finite additivity, and so on. But we only considered up to now elementary subsets of Rn. Now we would like to enlarge our collection of subsets to which a notion of measure can be applied, and for this reason we will now consider more subsets of Rn, bounded subsets, which can be approximated by elementary subsets, and we will see that once we have the right notion of approximations, then the new measures that we can define, these are called the inner and outer Jordan measures. They they inherit the nice properties of the elementary measures, such as translation invariance and finite additivity and finite subadditivity. So in this lecture, first before going to the inner and outer Jordan measures, we will see that the way we have defined the elementary measures on elementary subsets of Rd or Rn, if you have any other map which assigns a numerical value, a positive or non-negative numerical value to an elementary subset of Rn, which also satisfies translation invariance, non-negativity, and finite additivity, then it is related with the elementary measure, but up to multiplication by a constant. So in that sense, our elementary measure is the unique measure up to normalization by a constant, which satisfies non-negativity, translation invariance, as well as finite additivity. This fact will be useful later when we study the Jordan measures. So once we have seen this uniqueness property for the elementary measure, we will then move to define what are the inner and outer Jordan measures, and then we will also define the Jordan measurable subsets of Rn. We will see that our inner and outer Jordan measures are always finite, and if these two numerical values are equal, then we call that set to be Jordan measurable. So let's begin with the property of the uniqueness of our elementary measure, but this holds only up to multiplication by a constant. So I will explain what this means and where is the uniqueness coming from. But first let me make a couple of notations that I will use later. So first is that let ERD be the collection of elementary sets in Rd for d greater than or equal to 1. So our calligraphic ERD is the collection of elementary subsets in Rd, and secondly I will denote R plus to be this semi-axis from 0 to infinity. This is the set of non-negative real numbers. So now recall that our elementary measure which I now view from this space ERD to R plus. So it takes as input an elementary set E, and it gives you the value ME, which is a non-negative real number. Now this elementary measure satisfied non-negativity, finite additivity, and translation invariance. So now if we suppose that if we have another such map which takes as input an elementary set and gives you an output in R plus, and it also satisfies non-negativity, finite additivity, and translation invariance, then we will see that these two that it will be related to the elementary measure by a simple multiplication by a constant. So let us state this theorem. So this is our theorem. It says that M prime is a map from the elementary subsets of Rd, elementary sets in Rd, to the non-negative reals R plus, which satisfies three properties. First is non-negativity, the second is finite additivity, and the third is translation invariance. So we have seen that our elementary measure satisfies all these three things, and now we are assuming that there is another map M prime which also satisfies these three properties. Then this theorem says that there exists a constant alpha M prime. So this constant alpha M prime only depends on M prime, such that for any elementary set E, so this is an elementary set in Rd, we have that M prime E is equal to alpha M prime times Me, and this is our elementary measure on the right. And we can even explain further what is this constant alpha M prime. So with alpha M prime given by M prime of the set 0, 1, so this is the hypercube 0, 1 in D dimensions. So 0, 1 D is simply the Cartesian product of the intervals 0, 1 in D dimensions. So our alpha M prime is simply whichever number you have assigned via M prime to this hypercube 0, 1 to the D. So let's see the proof. I will only prove it for D equal to 1 again. So for the real line, for subsets of real line, and I'll leave the general proof for arbitrary dimensions as an exercise. So let's do this for D equal to 1. So first, suppose that our E is the set 0, 1 by n for some n, some natural number n. Now let us write our set 0, 1 closed at 0, open at 1 as the following union. I take 0, 1 by n, union 1 by n, 2 by n, union 2 by n, 3 by n, and so on. And the last one is n minus 1 by n and n by n, which is 1. So what I am doing here is breaking up the set 0, 1. So we have this set 0, 1 which is open at 1 and closed at 0, and I am breaking it up in chunks of size 1 over n. So this is 1 by n, this is 2 by n, 3 by n and so on, n minus 1 by n. So each one has size n by n, and here I will use the translation invariance of m prime. So using the translation invariance of m prime, we get that m prime of this set 0 1 by n is equal to m prime of any set k by n, k plus 1 by n, where k ranges between 1 to up to n minus 1, because it is just translating by this number k by n. So if you translate this set k by n to k plus 1 by n, so translate this set by the number k over n, one gets 0 1 over n. So by translation invariance we get that the m prime of 0 1 by n is equal to m prime of each chunk that appears in this decomposition. And now note that all these are elementary subsets of R, and this is a disjoint union. Therefore, now I am using finite additivity property. So by finite additivity we have that m prime of 0 1, which was m prime of union k by n, k plus 1 by n, k equal to 0 to n minus 1, and this is a disjoint union. So this is simply by finite additivity property, k equal to 0 to n minus 1, m prime of the set k by n, k plus 1 by n, and so we have that each set in this sum is the same as m prime times m prime of 0 1 over n, just by translation invariance that we have already seen. Translation invariance, and now you have the sum ranges from 0 to n minus 1, so you have n terms. So therefore this is n times m prime of 0 1 over n. Therefore we get m prime of 0 1 over n is equal to 1 over n times m prime of 0 1. Now this was our alpha m prime. For the case d equal to 1, this is our alpha m prime, and this is nothing but m of the set 0 1 over n. So this is nothing but alpha m prime times m of 0 1 over n. So for this set E, we get our required result, which is that m prime of E is equal to alpha m prime times m of E. Now I am going to do the same thing but for the set. So now take 0 p over q. So we have done it for 1 over n. Now we are going to do this for every positive rational p over q. So here p and q are greater than 0. So this is our E now, and now what I am going to do is take this set 0 to p and now I'm going to divide this in chunks of length p over q. So this can be written as a disjoint union p over q, 2p by q, union 2p by q, 3p by q, and so on, and you will end up with a interval q minus 1 by q times p, and then q by q times p, q by q times p, which is nothing but p. So this is now a disjoint union, and again we will use the same trick to write m prime of k by q times p, k plus 1 by q times p. This is the same as m prime of 0 p by q by translation invariance. So therefore, if I try to compute the value of m prime for the interval 0 p, you will get the sum from k equal to 0 to q minus 1 m prime of k by q times p to k plus 1 by q times p. So it begins at this interval. When k equal to 0, you will get 0 to p by q, and at the end when k equal to q minus 1, you will get this interval, which is q minus 1 over q times p to p. Now each of these is equal to m prime 0 to p by q. So therefore, since you have q as many terms, so you will have m prime q times m prime of 0 p by q. Now for the left hand side, we can divide it in another way, which is, so here of course p and q are natural numbers, because I am only considering rationals p by q, so p or q are natural numbers. So I am also going to write down 0 p as 0 1 union 1 2 union up to union of p minus 1 times p minus 1 up to p. So this is again a disjoint union, and so if you use translation invariance and finite additivity, you will get that m prime of 0 p is now p times m prime of 0 1. So by these two decompositions, we will have m prime of 0 1 times p equals q m prime of 0 p by q, and these are both equal to m prime of 0 p. Now I am only going to consider the first equality. This implies that m prime of 0 p by q is equal to p by q times m prime of 0 1. Now again we have this alpha m prime, and this is the elementary measure of the set 0 to p by q. So this is again alpha m prime multiplied by the elementary measure of 0 p by q. So first we did it for 1 over n, now we have done it for p by q, and our next step will be for any real number, any positive real number r. So let's do this for any positive real number r. B a positive real number. So for this one we cannot use this finite additivity directly, so we will use an approximation argument. So for this, suppose that we have a number epsilon greater than 0, an arbitrary number which we can make as small as possible. Now by the density of rationals in the reals, there exists PQ greater than 0 natural numbers such that R minus P by Q is less than epsilon. So we are choosing here, so this is our number R, and here we are choosing P by Q, and this distance is less than epsilon. So let's say this is R minus epsilon, so this distance is less than epsilon. So we can do this for any arbitrary epsilon because of the density of rationals in R. So this is due to the density of rational numbers in R. So now by monotonicity, remember that our M prime also satisfied non-negativity and finite additivity. So this is the monotonicity property can be inferred from finite additivity and non-negativity. Just as we did for the elementary measure, we can also do it for our new map M prime. So we can prove the monotonicity property of M prime. Therefore, since this interval 0 to P by Q is a subset of the interval 0 R, we have that M prime of 0 P by Q is less than or equal to M prime of 0 R. Now we already know what our M prime of 0 P by Q is. This is nothing but alpha M prime times P by Q. So we have M prime of 0 R is greater than or equal to alpha M prime times P by Q. But note that we have chosen our P by Q such that P by Q is greater than R minus epsilon from this choice. Therefore, this is greater than or equal to, so you can even write greater than or equal to, so alpha M prime R minus epsilon. Similarly, there exists P prime Q prime greater than 0, P prime Q prime in N, such that you have M prime of 0 R. Well, first of all, let me write P prime over Q prime minus R is less than epsilon. Now I have chosen approximated this number, real number R, from the right. So in this picture you have P prime by Q prime, this is R plus epsilon. So this is again less than epsilon. So the distance between P prime over Q prime and R is less than epsilon. And again I can do a similar analysis. So by monotonicity, we get that M prime of 0 R is less than or equal to M prime of 0 P prime by Q prime now, and this is nothing but alpha M prime times P prime by Q prime. But since we have chosen P prime by Q prime minus R is less than or equal to epsilon, so this is less than or equal to alpha m prime times r plus epsilon. And we have already shown that this is less than or equal to alpha m prime times r minus epsilon. So we have seen this kind of argument before, where we approximate from both sides. And since epsilon greater than 0 was arbitrary, we get that m prime 0 r is equal to alpha m prime times r, because this number alpha m prime times epsilon is also arbitrary. So now we have proved our, of course this r can be written as m of 0 r. So now we have proved it for any interval of the form 0 r. Now this easily implies for any interval I of the form AB, then you can shift by translation invariance, you can shift the starting point to 0. So by translation invariance m prime of I is equal to m prime of 0 b minus a. I am just shifting by a. So if you subtract a on both ends, you will get 0 and b minus a. And this is nothing but alpha m prime times b minus a, because b minus a is any real number, and this is alpha m prime times m of I. So therefore we can do this for any interval, and now the only thing left is to show this for any union of intervals. So suppose that E is elementary. So then remember that in the previous lecture we proved that there exists disjoint intervals I1, I2, Ik, such that E is a union of these i's from 1 to I equal to 1 to k. So now this is a disjoint union, and so therefore m prime of E is equal to the sum I equal to 1 to k m prime of I by finite additivity again, finite additivity property of m prime. But now we know that this is equal to alpha m prime times m of I, and this is alpha m prime, and by the finite additivity property of our elementary measure, this is simply m of E. You can take this constant outside the summation. So we have shown that m prime of E is equal to alpha m prime of me, where alpha m prime is simply the value m prime of 0, 1. And this kind of argument can be generalized to arbitrary dimensions, but there you have to be a little bit careful, because you have to chop your any box into many chunks, each having side 1 over n. So dimension D greater than or equal to 1, this is left as an exercise. So for example, in dimension 2, if you have a box of size so let's say this is 0 1 over 0 1 cross 0 1, then you have to chop this up into size 1 over n in the y direction and also in the x direction, 1 over n. So now you have each box has the same value m prime for any of these boxes that appear in this grid form. So this is not very difficult, and I leave it to you as an exercise for any dimension d. Okay, so now we have seen that our elementary measure is unique up to multiplication by a scalar c,